Good afternoon, everyone, and welcome to today's session of Sunoikisis Digital Culture Heritage. Our class today is about network analysis, and I am very, very happy to introduce our speaker for today that is very bravely doing a solo class, and is Tom Brughmans that is based at Oxford, and I am just going to hand it over to you, Tom, and tell us everything about network analysis.
Thank you very much, Valeria. It's a pleasure for me to teach this class. I'm really looking forward to it, mainly because I do nothing else but network science in archaeology. It's literally been my only professional occupation for the last 10 years. And this is rather a rare thing to do, so I'll try to convey a little bit of that passion to you. If not, just turn off YouTube. So what I'll try to do in this lecture is first give you an idea of how archaeologists, historians, and classicists have been applying network science to their research, the different kind of phenomena that we use network science for. Then I will give an explanation of why network science does things that we can't do with other techniques that we use more frequently in archaeology, history, or classics. And then I'd like to switch to a practical example using the software called Visone, which I like a lot because it's really very reliable for the statistical measures that are included there. And it does just about anything you really need to be able to do if you're starting network science. Also, that piece of software is the one that is used for the exercises in this class. Okay, so without further ado, I'm going to share my screen. And I'm going to start my presentation. So an introduction to network science. When I say network science, I really just mean the use of points and lines for studying some sort of phenomena. As archaeologists, historians, classicists, we study past phenomena to do with human behavior. We study how humans behaved in the past and how that behavior changed. And when we say we apply network science for that, then we basically say we use points and lines for representing our sources, our data of those past phenomena, or for representing our theories that we formulate about those past phenomena. How did past humans behave? How did they interact with one another? Can we represent these humans as points? Can we represent their interactions or their potential for interactions as relationships? Can we represent our sources about those humans as points, and perhaps the ways in which those sources are similar as relationships? In order to do that, it's really simple. You need to define two things. On the one hand, a set of objects. These are the individual bounded entities that are the focus of your analytical work. In the case of the example network you see there, we can say that the objects are humans. They're individuals, and they have a name. It's Tom and Simon. Tom and Simon are the nodes in our network, and that's network jargon. The points are called nodes. The second thing we need to define is a set of connections, relationships. Those connections in network jargon are called edges. So in the case of our example here, Tom and Simon are connected by a relationship because they are colleagues. Tom and Simon work in the same university. However, we can specify the nature of that relationship by, for example, assuming that there's some sort of hierarchy or directionality to the relationship. Simon also just tends to be my supervisor. Well, when I was doing my PhD, Simon was my supervisor. So there's definitely some sort of hierarchy there. And we can represent that by creating a relationship that has a direction. Simon supervises Tom. That's really all there's to it. Then the difficult bit is to really think about what are the past phenomena that you're trying to study. Are you thinking about transport systems? Are you studying past social interactions? Are you studying urbanistic environments? And how is it appropriate to represent some parts of that phenomena as nodes and other parts as relationships? So I want to give you a couple of examples of the main fields of application of network science for the study of the human past. First group of applications is road networks. They are transport systems where very often the individual settlements or stopping points or crossing points of roads are represented as nodes, and the roads themselves are represented as lines. An early example of that is a study by Leif Isaacson, which he published in 2005 and again in 2007. He studied, we were looking here at a map of the south of Spain, of the present-day province of Andalusia. It was the Roman province of Baetica. And he mapped all of the roads that occurred in two different sources. The Antonine itineraries, which are a list of itineraries of how you can move from one place to another along a Roman transport system, and also the Vicarello goblets, which do the same. So two basically historical sources. The Antonine itineraries are the red lines you can see there. The blue lines are the Vicarello goblets, or maybe they are the yellow lines. There was a third source, actually, a cosmography. What he then did is combine also those navigable rivers in this particular province, also assuming that you could move from one town to another town if they are connected by a navigable river. And in the case of Roman Baetica, that's just two rivers. We have the Guadalquivir River right here, which goes from Cadiz past Hispalis, present-day Sevilla, and then goes to the Atlantic here. And then here we have the Genil River. So there's just two little stretches of those rivers that are navigable, and they are connected by these green lines. Now, by doing that, by representing the towns as nodes, by representing the roads and the rivers as relationships, Leif Isaacson could do a couple of really interesting things. He could explore which ones of these towns are connected by more roads and rivers than any of the other ones. Which towns are more directly accessible from their neighboring towns? And which towns are really hard to get to in this particular province? For which towns do you have to pass through a lot of rivers and road sections and a lot of other towns in order to get there? Which of these towns are the most central ones and which ones are the most peripheral ones? And that's an interesting thing. Now, if you scale that concept up, you get Orbis. Orbis is a small project that was led by Walter Scheidel and implemented by Elijah Meeks and a group of colleagues at the University of Stanford. Now, what they did is really just create a Google Maps of the Roman world, which is, of course, really cool. They took this subset of, I think, about 800 urban settlements in the Roman world. They then connected those settlements with known roads, as referenced in the Barrington Atlas of the Greco-Roman world. And they then also ran simulations for representing the most likely or most important maritime connections between the port settlements. And then you get a network map, which you can do a lot of fun things with. You can calculate how to get from Antioch to Corinth, for example, in the summer season, select the fastest road, and choose to only travel by donkey, for example. These really important historical questions you can ask with Orbis. So you can clearly see that, it's a fun thing to play with, and I definitely recommend you going to the Orbis website. Just Google Orbis Stanford and you'll get it. It's a really fun thing to play with and a good example of trying to get your head around how network science can be used in practice. Now, a second group of application is for the study of material culture similarity or historical source similarity. Now, especially in archaeology, this is a field of application that has received a lot of attention because it's really close to what we tend to do as archaeologists on a daily basis. So what I mean by similarity networks in an archaeological context is if we consider, like in this example, two sites. We have site 1, so an archaeological excavation 1, and the second one. At each of these sites, a couple of artifact types are found, in this case, ceramics. So in site 1, we found pot type 1, and in site 1, we also found pot type 2. In site 2, we only found pot type 2. We could represent these archaeological assemblages of the sites and their similarity by drawing a line from every site to the pot types that they have. And then assuming there's some sort of similarity between the assemblages of the sites based on the pot types that are found there. So site 1 and site 2 have a similarity of 1, if we just consider the presence or absence of these pot types, because they have one pot type in common. Now, this is something that we do a lot in archaeology on a very large scale, and we try to identify those groups of sites which have more artifacts in common than other group of sites. And we formulate theories about why that might be the case. Maybe if some sites have more artifacts in common, then in the future they tend to become also more common with other artifact types. So we could formulate theories about how their similarity could evolve in the future. Maybe that similarity represents more frequent contacts between the communities living at those sites. Maybe they tend to exchange similar cultural ideas and tend to have the same taste in products, for example. All these kind of theories that archaeologists formulate a lot when they excavate stuff. Now, you can supercharge that idea by taking all of the archaeological data that you can tend to find on a Roman site, for example, and making loads of networks out of that. So here's something that we did a while ago, where we were just really trying to push this idea to the limit. Like, what kind of archaeological similarity networks could we make given the data that was available to us? And this led to a really interesting exploration of a large data set. So we are looking at loads of different data types. We had access to ceramics, to architecture, to Roman coins, Roman roads, the ones you saw earlier, evidence of people who were foreigners in the place where the evidence was found, inscriptions, benefactions, weapons, monuments, sculpture, visibility in the landscape, and summing all of those things up. This concept of similarity networks could be represented for each one of these data types. And for each one of these data types, we also had information about the different chronological time periods at which they were found or to which they were dated. So all of this allowed us to explore these networks of what was found on a single site, what was found on multiple sites, how similar multiple sites are, and for the entire data set as a whole. This was really kind of a really nice way of using network science for exploring a very rich data set, for exploring our theories of what it means for sites to have similar assemblages based on certain artifact types, and to see how those things changed over time. For example, what we noticed is that for the case of visibility, how visible the particular settlements were, this is something that's emphasized as a really important thing in Iberian times, in the Iron Age times in southern Spain, but it's not emphasized as an important thing in Roman times. Now, we noticed that there's a lot of similarity in the visibility signature of sites in Iberian times, but there's a lot of that still remaining in Roman Republican times and early imperial times. And this is something that was rather counterintuitive, and it's a result that we obtained by doing this exploratory network analysis. Moving on, we can use network science for representing our theories about past phenomena. Here's a really good example, Anna Kollar's study of the cult of Jupiter Dolicanus, and she formulated the theory that this particular cult in the Roman world tended to spread following a geographical logic. The ideas of the cult tended to spread from one place to its three nearest neighbors primarily, rather than to places that are further afield. So she represented that by taking a set of sites or urban settlements from the Roman world at which evidence of the cult of Jupiter Dolicanus was found, and then connecting these each site to its three nearest neighbors. By doing that, she gets a network, and that was a representation of her theory of how this spread. So some of these nodes in the network, some of these urban settlements turned out to be very central, turned out to be very well connected in the entire network, and were very close to all of the other nodes, whereas others were more peripheral. By combining that with information from historical sources and archaeological sources about the dating of certain evidence of the practice of the cults, she could also add a chronological perspective to it and explore how, from one side of the network, the ideas about the cult spread to other parts of the network, and perhaps how geography structured that. Final bunch of applications in classics and archaeology is the use of network science for studying social networks, past social networks. Now, this is particularly challenging in archaeology because we tend not to have access to humans in the past. However, some people like Sean Graham take really creative approaches to it. What Sean Graham did is take a set of bricks, so literally just clay-baked bricks from the Tiber Valley in the area of Rome, and he collected 3 types of information from them. On those bricks, very often they have a stamp, and the stamp has inscribed information about who produced it, about the potter. You could look up where that potter had his workshop, where the workshop was located. And so the potter's name, in addition to the potter's name, you could also identify who owned the plot of land on which the pot was produced. You could also look at the chemical signature of the clay from which the brick was produced and try to identify what the source was of that clay. Where on the river Tiber Valley was this clay sourced? If you can identify who owned a plot of land from where the clay was sourced, then you have a third name. And that's what Sean Graham did. Really creative. Now, if you have those 3 names for thousands of bricks, you can create a social networks of Romans in the past who were active in Roman brick production and trade. And this might sound like very mundane, but actually the results were, again, really surprising. One of the people that he found to be extremely central in this network was the wife of one of the emperors in the early imperial period. So this was really kind of like an archaeological representation of something that is not really emphasized a lot in Roman studies, that people in the top echelons of in Roman imperial times really did get their hands dirty with trade, with commerce, with things that are so mundane but so lucrative as just the production of bricks. And here's a really early example by Alexander and Danowski from 1990, in which they took Cicero's letters and they represented the people that Cicero knew and wrote to as a network. So those numbers that you can see there are people, and they write letters with each other, and they know each other. And so you can kind of like explore the ego network of Cicero, if you will. Cicero at the center and the people that he knows, and what's the structure of his direct environment as reflected by his letters. So that's just a bunch of archaeological and historical applications of network science. Now, what's really important to realize at this point is that in all of those cases, interesting results were obtained, but not because we could just represent stuff as points and lines. We didn't use network science in these cases because we could, but because we had a particular theory about the past phenomena we're studying. So in network science, it's really important to realize that the phenomena we're studying, like in all archaeology and classics in history, right? We are not directly studying those past phenomena. We are not directly studying past road systems, or we're not directly studying Cicero and his social contacts. We have sources to study those things through. And so that distance forces us to abstract the phenomena that we're interested in. We are forced to abstract Cicero as a dot. Cicero is a dot, is a bounded entity for analytical purposes. And what we can do if we formulate theories about how the relationships of Cicero are important, then we use network science concepts to do that abstraction. So it's appropriate to represent Cicero as a dot if we formulate theories about how he related to other people, and if that's important for better understanding this past phenomenon. The past phenomenon being Cicero's life and works and his relationships with other people as it's reflected through the historical sources. Those network concepts, the points and lines, the entities and the relationships, can be represented using network data in network science software. We can use different network analytical techniques to say something about those network data structures. That's what we do with network science. We don't study these past phenomena directly. Instead, we study either the structure of our sources or an abstraction of our theories about how a past phenomenon functioned. And you can apply that concept to loads of different phenomena. So the study of trade, transport systems, exchange, visual signaling, island community interaction, urban spaces, social networks, you name it. Just always, when you try to make a network out of your data or out of your theory, just always try to think, why am I doing this? Do I have a theory about why relationships matter to the phenomena that I'm studying? If the answer is yes, then network science is what you should do. If the answer is no, then you might as well drop network science, but it's been a very productive afternoon because you know what you shouldn't spend your time on. Now, here's an example of these network theories, these kind of theories about why relationships matter to a particular phenomena. We are looking, say, at an abstraction of a past road system, a transport system. Every node represents a town, and we have 3 towns, so town A, B, and C. And the towns are connected by roads. So from town A, you can move to town B, and from town B, you can move to town C. Now, in this first part of the figure on the left-hand side here, let's assume this is the starting point. This is the first phase. We can formulate theories about why these relationships matter. We could, for example, formulate the theory that if you are more central on this transport system, if you can mediate the flow of information, goods, money, people between other towns, then you are more powerful. For example, town B is in a particularly special position here because it's the only town that mediates the flow of goods, information, and people between town A and town C. All of the transport from town A to town C has to pass through town B. Now, in light of our theory, that makes certain things, the expressions of their power particularly interesting to study. Do they levy particular tolls, to kind of make use of that position of power? Or are they particularly nice to their neighbors, and do they, really encourage them to use the roads that connect town A and town C? It could be, however, that in light of that situation of power of town B, all of a sudden the people in town A and town C say, well, I'm sick of this. Let's build our own road. Let's bypass town B because I don't want to pay tolls anymore. So then we go to a second phase of our example here, where there's a direct road connecting town A and town C. This, again, the move from example A on the left to example B on the right is a representation of a network theory, but a network theory not about the properties of those nodes and how important the structural position is, but rather about how the network structure changes over time in light of our theories. If we formulate the historical theory that if town A and town C find themselves in a disadvantageous position, but they want to trade with each other, then there's a higher probability of creating a road that allows for that trade. This road is created because in the previous phase, we had this network structure. This is an example of a network theory. It's an archaeological or historical theory, but it's represented using network concepts and network data. So to come back to the point of network science in archaeological historical research, if you can answer the question, do relationships matter for the study of a past phenomena? If you can answer that question in light of those 2 examples I just gave, then network science is what you need to do. Network science offers you a bag of concepts, of techniques, of software, of ways of visualizing your data, and ways of deriving some analytical results that allow you to express your theories, that allow you to study your data, that allow you to come to new insights about the past phenomena you're studying. So, the potential of network science, therefore, is the formal study of your theories about the importance of relationships, and it's not a hammer that we use just because we have it. Now, this is time for some shameless self-advertising. This kind of argumentation about why we do network science in archaeology and history is published in this book called The Connected Past, and also in a special issue about network science in archaeology in the Journal of Archaeological Method and Theory. So, of course, I would recommend those publications. I'm now going to stop sharing my screen and show you a couple of other resources that might be useful. So I'm not sure if I'm visible. I think I am, but
yes, you are.
Oh, that's great. So here's that book that I was so shamelessly self-advertising. I like it, but it's one of the few books that really tries to identify all of those challenges that I was formulating about why should we do network science in archaeology and history. So The Connected Past. In addition to that, another good book to give you an idea of why doing network science in archaeology is this one, An Archaeology of Interaction by Carl Mappett. We also have Network Analysis in Archaeology, which gives a lot of examples of applied network science in action in archaeology on a regional scale. Now, network science is not something that was invented by archaeologists or historians, but there were two main disciplines from which archaeologists and historians kind of got their ideas, and which have a strong research tradition in network science. The oldest one of those is sociology, the subdiscipline of social network analysis. They've been working on this stuff since the 60s in a very formal way. And the main reference book in social network analysis is this one. It's published by Wasserman and Faust in 1997. And it's really a Bible. It really has everything you need, but can also be a little bit daunting to access. But if you want to get serious with network science, I do recommend this book. Then here's another book in social network analysis, and this was actually my first way into doing network science in practice. I am not a network scientist by training. I'm an archaeologist who likes to use computers, and it was very difficult and challenging for me to kind of like find a good resource to learn network science and to be critical about network science. I started playing with the software Payek. And this book is a manual on how to do exploratory network analysis with Payek. It is really very accessible. It has loads of good examples, and it's really easy to read. It's strongly tied to a software package, which in this case is very appropriate. It's also a really great source for easy to understand definitions. So I can definitely recommend that. The second subdiscipline from where archaeology and history got their ideas is the study of complex networks in physics. One important book that is a very good reference work is Networks: An Introduction by Mark Newman. Again, it's really comprehensive, but it focuses more on not just social networks, but kind of fields of application beyond social science, in biological science, in neuroscience, absolutely everywhere. It also focuses way more than the sociologists on dynamic network models and random graph models and these kind of things. A really good book. And then an alternative to that is Ernesto Estrada's work on complex networks, equally comprehensive, and they tend to complement each other in their coverage. Actually, I mean, they both cover the basics, but they give a different argumentation for some network metrics. Okay, then I'm going to share my screen again because I want to show you a couple of resources that are online before continuing to a practical example. So if my screen is correctly shared, which I think it is, we here have the Historical Network Research website. This is a really great resource for archaeologists and historians. They organize yearly conferences, which I recommend you go to, as well as workshops. There's also great resources. So there's a first steps tutorial, but there's an entire list with tutorials and links to tutorials. So if you are interested in a particular aspect of network science and you're a historian or a classicist, this is a fantastic resource. Their bibliography is also great. It's an open Zotero bibliography that is continually updated and has a lot of different sections. So about ancient history, early modern history, art history. It's really comprehensive. And that brings me to my own blog, Archaeological Networks. This is a good place. So it's archaeologicalnetworks.wordpress.com. And this is a good place to find tutorials and resources and bibliography for archaeologists. So here we have the tutorial that I recommend you do as an exercise. If you click on the Tutorials and Resources tab, the first one is Network Analysis with Visona. And Visona is a software we'll be using in a bit. This is really a step-by-step tutorial, but there's many other tutorials that use NetLogo for agent-based modeling and network science, importing a Roman transport networks, doing sensitivity analysis and statistical techniques. This is using R. So a lot of cool stuff. And I've also got network bibliography on there. Again, it's a Zotero bibliography, and this is an open one to which everyone can contribute. It's important to state that this is also included in the historical network research bibliography that I showed you earlier. So if you want everything in one place, go to historicalnetworkresearch.org. The final thing I want to highlight is the Connected Past, connectedpast.net. This is another community like the historical network research community, focused maybe a little bit more on archaeologists, but it organizes yearly conferences And this year, this will be held in 2 weeks' time in Oxford. It tends to be very multidisciplinary and have a lot of great examples of archaeologists, historians, classicists presenting their work and discussing how they can do network science constructively together. Now, I will continue with the practical side of this lecture. So what I thought would be really useful is to kind of show you one of those fields of applications I showed you before, but in practice, and how you could go about doing that for yourself. I will do that using Visona, the software that I also recommend for the exercises. The field of application I'm talking about is transport networks. So the data source I'm using is represented here on Pelagios. So if you go to commons.pelagios.org, on Explore Data, there's this great Roman world map, which is a really fun thing to play with. A lot of the data here is from the Ancient World Mapping Center, and you can see, you know, the geographical representation of the Roman world. These red lines here are what I'm interested in. They are major roads in the Roman world, as represented in the Barrington Atlas of the Greco-Roman world and as digitized by the Ancient World Mapping Center. Now, this data can be downloaded and you can make network data out of that. And I will show you how you can play around with that network data. So what I'd like you to do when you do the exercise is to download Visona. And that's all described. How to do that is described in the tutorial. When you open Visona, you see this here. This is the interface. So it's got a graphical user interface with buttons for absolutely everything. So there's no scary code involved. And it's really quite intuitive. You can make a network really just by sketching it out. If you click this red pencil here, you can just click, and that's a bit big, and make some nodes. So let's make 4 nodes, for example. And then if you click on the node, you can create a relationship. You can create an edge. So let's connect these nodes up like this. Okay, and I very quickly made my own first network. What's also a really nice feature is that on the top right-hand corner, you have this button that instantly creates a layout to make it more visually appealing. So if you click this, you can see the structure of that network a little bit more clearly. It avoids overlapping the nodes, the labels, the edges. The important bits of Visona are on the left-hand side here. In the Analysis tab, you have all the analytical tools. So if we want to, kind of describe the structural features of our network, for example, we can look at the centrality of the node and look at the degree centrality. Degree centrality is really just the number of links that are related to a node. So in the case of this node here, the one in the center, we expect the degree centrality to be 3 because it has 3 relationships. 1, 2, 3. So we accept these default settings and we click Analyze, and that analysis has been performed. If you want to see the results of that analysis, then we have to click here on this Attribute Manager. In the Attribute Manager, in the Node tab, we see the attributes, the information of the network data. So we see a list of 4 nodes which have unique identifiers, 1, 2, 3, 4. And we see the degree of those nodes, in this case represented as a percentage. I'll do that again just to show you what this would look like without selecting percentage. So this is perhaps a bit more intuitive. We have degree as represented in absolute numbers. So node 1 has degree 3, that would be this one here in the center. If I select it, you see that only that node is shown here. If I deselect it by clicking anywhere else, you see all the results again. And this node has a degree of 1, it only has 1 relationship. You have loads of different types of measures. Then we can visualize that information on the Visualization tab. We can map the color to the nodes. So for example, I could change the color of the nodes according to their degree. So I select this and I click Visualize at the bottom here, and then the nodes, well, this is not very intuitive. I'm going to have an interpolation just so I have a maximum results that are darker blue and minimum results that are light blue. If I click visualize, I see immediately that this node in the center here has a higher degree than these nodes, which have a higher degree than this node. I can also map that information to a different variable, to the size of the nodes. So I'll just go ahead and do that, see what that gives. And so it scales the size of the nodes to their degree. So this big one at the center here has a higher degree than this little one on the right. Now, what can we do with this if we have this road data set that we were looking at earlier? Let me just show you that again. So we have, first thing we need to do when we want to get this data set is to think about what are our nodes and what are our edges. So because I talked about this before, it's quite intuitive to consider the towns, the urban settlements, the Roman settlements in this particular system as the nodes, and to have edges in every case where a pair of urban settlements is connected directly to each other with a major road. If we do that, then we get a network like this. So these are just those red lines that you saw earlier, but now not represented in a geographical way. So you're still looking at the Iberian Peninsula, but what we've done instead of representing this geographically is to represent this topologically by clicking this button here on the top right. We position the nodes in such a way that all of the lines avoid overlap with each other and that all of the structural features we see here are as clear as possible. For example, all of the isolated nodes, all of the towns that have no roads connected to any other towns are positioned at the bottom. We also see that towns with a low degree, which are very peripheral, tend to be at the outside of the network. And we have a couple of clusters that are highlighted at the center of the network. So we can do a couple of analyses with this network and try to identify some structural features of the Roman transport system in the Iberian Peninsula. So let's do that. The first thing I tend to do is to start on the level of the network as a whole. So what are the key structural features of the entire network? You can do that quite easily in Visona by selecting indexing here and then selecting the class network. And it just calculates a couple of very common network statistics. Those statistics that you tend to find in all publications of network science. If I click apply, it calculates this. And again, the results are shown in the attribute manager, but this time in the network tab. So we can interpret these results now. We have a measure called the average degree. And the average degree is really just the degree of every single node. So how many roads each town is connected to. All of that summed up and divided by the number of nodes. So the average of the number of roads for every node. And the average of the network is 2. So on average, every urban settlement here is connected by 2 roads. Now, is this interesting? On its own, perhaps not. Maybe, unless this is a surprising result, unless you expect every town in Roman times to be connected to 1 million roads, then, that is a surprising result. But these kind of network measures are really most interesting when you compare different networks. So this kind of gives a statistical snapshot of a particular structural feature of this network. Whether it's meaningful or not, it's definitely interesting to compare it with other networks. What, for example, is the average degree of the Roman road network in Italy or in Gaul or in Britain, for example? Do they have the same kind of structural features on the network structure, on the network level? What if, for example, we would have chronological information about the Iberian road network? Do we see a change in the average degree from the early imperial times to late antiquity? Would we expect to see that change? That's what you tend to use these network measures for. Let's now do some node measures. That's the second thing I tend to do. So centrality is an example of a node measure. We calculate something, some structural property of a node rather than of the network as a whole. So the degree of a node is a structural property of that node. It says something about the structure of that node in the network as a whole. We can again calculate the degree for this entire network. And then we see it here on the node tab. There's a lot of attributes in this thing here, but we have a degree here. We can rank it and see that the highest degree in this network is 9, which is for this site here. And the lowest degree is 0, and that's for the isolated nodes. We can again visualize that by getting these results, understanding them a little bit more clearly. So let's represent size as degree. So we see that the big nodes are these ones here. To emphasize that a little bit more, let's change the color to degree as well. So the dark one here now jumps out as the most central one according to the number of towns it is connected to. And that would be Merida. So that's Emerita Augusta, present-day Merida in the south of Spain, south of Madrid. So now let's try another measure of centrality. Degree centrality just tells you something about how many other towns are close to one town directly, if you can only move one hop over the network. But it doesn't say anything about all the movement that is possible throughout the network as a whole. How central are these towns, for example, to control the flow of information or goods or people in this entire network? Or how close is every town to every other town in this network? To do that, we use these measures called betweenness and closeness. So betweenness gives us a measure of how important a town is as an intermediary by calculating all possible shortest paths through the network and counting how often every node is positioned on those shortest paths. So if we analyze that, we'll also do closeness centrality. Closeness centrality represents how close every node is to every other node by, again, calculating every shortest path from that node to every other node and summing that up. And those towns that have the shortest summed path to all other nodes are closest to all other nodes. So imagine, this is kind of like the idea of if I am in Barcelona, for example, in Roman Barcelona, and I want to go to Roman Saragossa, how close am I to Roman Saragossa? Am I closer to every other place in the Iberian Peninsula if I'm in Barcelona or if I'm in Saragossa? This is the kind of questions you can answer with closeness centrality. So let's analyze that and let's again visualize that. So it's interesting to kind of like compare the results of these different analytical measures. These are different representations of how central, how important these different nodes are. So we change for the color mapping, the degree to closeness, and we visualize it. And then we see, I didn't change the size here, so just look at the color. But you see something really obvious here. You see that the darkest nodes are those nodes in the center of the network. Let me also map the size to closeness, so it's emphasized a little bit more. So we can see from the size and the color that there's not a huge difference in the centrality, but that just has to do with the absolute numbers of how it's calculated. But we do see a difference between those urban settlements in the center, which are closer to get to all other places than those settlements in the periphery, especially those that are particularly peripheral, like these ones here. Now, I expect betweenness centrality to show us something different. So we'll visualize both size and color as betweenness centrality. And this is a result. So this is quite different and more in line with what we saw with degree centrality. There's a couple of sites, again, in the center that are far more important as intermediaries than any of the other sites. This might be Saragossa. This site is probably Emerita Augusta, and a couple of sites in between them. This represents that these sites are more often positioned on paths between all nodes. So if you want to control information or if you want to extract a toll or these kind of things, and you consider only the road network, no other ways of getting there, right? Then betweenness centrality is the good representation of that. And these nodes are the most important ones in the Iberian Peninsula. Okay, that's just a very quick example of how to use this software. There's other useful tabs here and other useful features. One of the things I like about Visona is that it allows you to export the data as a couple of different formats. So as images, but also as vector formats, in CSV files, and in a couple of different network formats. You will notice if you start doing network science that that's a really important thing, because there's a lot of different types of software for network science, but there's not one canonical software that includes everything and that does everything. And so interoperability between different software platforms is a real problem with network science still. So having as your main go-to software a piece of software that's not only intuitive but also allows stuff to be imported and exported in different formats is really useful. And Visona is not too bad in that. It also has a useful import format. So if you open, it's really quite intuitive. If you open it, you can create a network and specify whether it's which type of site it is. Then you can specify which data format the network data is formatted in that particular document you just opened, and create a network from it. It kind of, through all these selections here, it guides you through defining what are the nodes, what are the edges, exactly how they are formatted, whether they're directional or not. Now, these are the kind of things that are explained in a lot of detail in the tutorial that is referenced in the exercises for this lecture, so I'm not going to go into any detail there. Okay, so that's all I wanted to say about that software. I'm going to stop screen sharing now. That was just a quick overview of network science in archaeology and history. On my final slide here, I'll share this again. On my final slide, I've got a couple of recommendations for network science in archaeology and history. So it's always, if you consider doing network science as a historian or as an archaeologist, as a classicist, always just think about why you're doing it. It's good to just explore something because you can, and to explore your data set in a different kind of context. But ultimately, when you get to the point of doing a serious study, you will want to have a very strong motivation why you're doing network science. And so I'm giving you the answer to that question. If you want to be sure that network science is something you need to do, then think about how important relationships are in your theories. What are your thoughts about how this past phenomena, whether it's Cicero's letters sending to other people, or people moving over the roads in Roman southern Spain, how important is the relationship between those towns in Roman Spain? How important are the relationships between Cicero and other people? What do you think about those relationships? Do you think that Cicero has a tendency of sending loads of letters to some people more than others? Do you think there's a trend in how he writes letters to people, that some people he writes a lot to at the start and others less so later? Do you think that's proxy evidence for perhaps his real life social relationships, or perhaps his professional relationships with the people he writes letters to? Those are relational theories. They are not network theories. They are theories about archaeology, about history, about classics. You are a specialist in history. You are a specialist in your data sets, and you are the best person to evaluate what those right questions are and what those relational theories are. But if they are relational theories, then network science is your way for representing and studying them. So stay an archaeologist, stay a historian, stay a classicist, and just use network science for what it's good at, which is studying relational theories. Now, always keep in mind that the issues that you have with archaeological data or historical data, all of your source criticism and stuff, that doesn't disappear as soon as you import the stuff in a computer. That's the case with any kind of formal method, and it's the same with network science. There's no way in which network science solves the issues that you have not enough data to study a particular phenomenon, for example. Network science results are equally sensitive to having incomplete or uncertain data as any other approach, qualitative or quantitative, is. So just always stay a critical archaeologist or historian when you're doing this stuff. When you are considering adopting a particular technique in a network science arsenal, then just always keep in mind what the technique is designed for, whether it's appropriate in your particular context, but also what the limitations are of the technique. So for the centrality measures, for example, I showed 3 of them, right? Degree centrality, closeness centrality, and between a centrality. the degree centrality only talks about the direct neighbors of a node in a network. So this is appropriate if you don't assume that people, things, diseases, religions can move over the entire system. But if you do assume that things can move through the entire system, so from node A to node B to node C, then perhaps these path-based measures like betweenness and closeness centrality are very interesting. So this could be seen as an advantage of betweenness and closeness and a limitation of degree. And depending on your archaeological or historical research context, one will be more relevant, more appropriate than the other. But you need to understand what the techniques do. You don't just, apply them. Then just always keep in mind that network science is something that's constantly developing and is definitely not canonical. Techniques are constantly being developed, and in fact, more and more often, archaeologists, historians, classicists come to physicists and computer scientists and tell them that the technique that they need doesn't exist. And this often leads to completely new techniques being developed. So if you have a problem and you look around in network science and you don't really find a solution, grab the first computer scientists or physicists at hand and just make them code the stuff for you. Very often it's something that's of research interest, not just to you for the study of the past, but also to other people in physics and mathematics and computer science. Okay. So with that, I'm going to conclude my lecture. Thank you very much for listening.
Thank you, Tom, very much. That was, that was absolutely brilliant. And yes, you did convey your enthusiasm, if you were wondering. Especially, I mean, besides obviously the great introduction to network analysis and network science that you gave, I was particularly happy about the very last points that you made, because I was really just about to raise those 2 points, and I would go with the first question if we have a little time. That is actually about, in a way, about transparency, but also about what you said about the fact that very often when we deal with classical and ancient data, the data are incomplete. So we don't make a network of all that we know about something. We make a network with the data that we have available in a digital format that deal with something. But because it is produced by a computer and it has the word science in it, I think that sometimes it may be misleading. It may give, and I mean, I'm saying this about a lot of digital outputs, not necessarily just network science, gives a false idea of completeness, of we know this for sure. So I deal with that a lot. For example, when I look at 3D representation, how do we convey either visually and in the dissemination the idea that this is not all we know, about everyone knows about it, that's all we know about it. So I was interested how professionals are like people like you that deal with network science. How do you communicate that, either visually in your final output, or in conferences, in publications, besides just saying, please guys, bear in mind that all data is incomplete?
Yeah, it's a really good question, because it is a really big issue, and the sad truth is that it's extremely rare to see a study, let's say, that's based on the exploratory analysis of an archaeological or historical data set that formally deals with this issue, that does more than just acknowledge somewhere in a sentence, oh, by the way, it's incomplete, guys, but that actually says my results that I present here are sensitive within these ranges to what I know of how bad my data is. Now, network science, like all formal techniques, is really good at hiding the incompleteness of stuff. So when I make this Roman Roman Iberian road network, it looks like, wow, it's all there. The same with the map on Pelagios. It just looks like, yes, we know what the roads were like in Roman times. I've got them there, and it just cascades from one source into another, from one analysis into another. This is why it's really important that we stay archaeologists and historians. We are trained very well to be extremely suspicious of our sources. That they're digital and not books, doesn't matter. We actually have a lot of tools available to us that are qualitative tools for criticizing the sources that we use, and we should keep on using them also when we do network science. Now, I would also say that the issues are exactly the same when you do informal approaches, when you use qualitative approaches. A book is extremely good at hiding stuff as well. And an advantage of formal approaches would be that at least if you share your information and you share your process, it is reproducible. It's in theory possible to identify where the bodies are buried. It's in theory possible to identify exactly how shit your data is. That's way more difficult to do with things that are just written down in a book. But obviously, in the humanities, a combination of the two is the only way forward. There's no healthy data critique without writing books. Now, the hopeful bit, there are loads of techniques in network science for dealing with this issue of incompleteness of your data, or of the uncertainty about how accurate some parts of your data is. And the most common thing to do if you want to formally address that would be to perform a sensitivity analysis. So a statistical evaluation of how sensitive the results are that you produced to the uncertainty that you know about. So one resource that I can recommend for that is to go to my blog, archaeologicalnetworks.wordpress.com, and on the tutorials tab, there's one that's called Statistical Sensitivity Analysis or something. It's created by Matt Peoples, and a tutorial made by myself and Matt Peoples, in which he explains in a lot of detail how to do this with R, in a case where we have an archaeological data set and we assume that half of it might not be correct. Like what are the impacts on between a centrality calculation, for example. And if you perform something like that, the results are often they help you to temper your certainty of certain results rather than others. They could suggest that, for example, between a centrality in this particular data set is very sensitive to the mission information, whereas degree centrality might not be. So in a qualitative way, you can attach more importance to your degree centrality results and follow, an interpretative line more based on a degree centrality than on the between a centrality. What's not possible is, using network science to create the stuff that's not there, so you're not going to create more data. What is possible is to fill the gaps with, interpolations and expectations in light of your theory. But really what goes in there is data critique and theory. And those things are archaeology and history. They are not network science.
Yeah, thank you very much. That was really useful. Can you see the question that Anissa is asking? Okay.
Yes. So, Anissa, thanks. A practical question, you say? Does Visona deal with a complex network where there are different relationships, the edges, between the same set of nodes? Yes, it does. So you can assume different types of relationships, and you would specify that by, in your input data, creating, a list of relationships and giving a different attribute to those relationships. So, for example, I gave the example of the Iberian transport system. I gave one set of relationships because they were all roads. But what if, in the case of Leif Isaacson's study, you also assume the navigability of rivers? So you would introduce a different set of relationships, and those would be the waterways. And you could distinguish between the two. In your input data, then you would just specify from Cadiz to Sevilla to Hispalis, you can go by road, or another relationship is you could go by water. And then you could explore those two sets of relationships independently. So what is the structure of the network when I just take into account the waterways? Or you could match them up together and just kind of assume, okay, well, you had, like in Orbis, you had the choice of moving over both roads and water, and you just do what's necessary, in light of your aims. So yes, Visona can do that, and it's pretty performant at that. I would mention that the way of dealing with multiple types of relationships, there's not loads of techniques there, so it's called multiplex networks in the jargon, and there's not loads of techniques implemented in Visona for doing loads of analytical things with it, but they do exist. But there's an important issue of how do you interpret it as an archaeologist and a historian? The concept of roads and waterways as different relationships and kind of considering them together, it's quite an intuitive thing to do. But what does it mean in an archaeological context? A pair of sites to be both intervisible and to both have the same type of amphory found at them. What does that mean? We are dealing with, we could represent that as a multiplex network. We have two different types of relationships, but how do you interpret that? Is it appropriate in that context, to scale that up to an entire region and to use between a centrality? How do you interpret between a centrality, based on artifact centrality and visibility merged up together? So it's really important to stay critical when you're doing these things. As humanities scholars, it's really tempting to put all of the qualification in a formal study that you want to put, because it's really difficult to hide the fact that you do know some things. I know these places were connected in this way and this way and this way, and it has to all be in there. But that does make it really difficult, to interpret results in a meaningful way. So very often it's more useful to just, start at the basics, study one aspect of your data, understand that very well, and then add another aspect, so complicate it a little bit, and then see what the difference is. So what are the effects of one relationship on adding it to the relationship that you already understand? So you can build up the complexity. But there is a reason why, this graph I showed you with the cube of like 1 million different archaeological data types and ways of doing networks in archaeology. There's a reason why I did that in the first year of my PhD and not, why I'm doing that now. It's very often more productive to stay very simple at the start and then build up the complexity.
Cool. Do we have any more questions for Tom?
I think I have a question. At least this may turn into a question by the time I finish saying it. So I really liked what you started saying, and you've been talking about for the last few minutes about how the selection of data and the preparation of your data is absolutely essential. And that's where, as you say, the historian and the archaeologist asks the questions that you're then going to put into your data science. And that's true of all the digital resources we've talked about, particularly any quantitative methods we've talked about, where data preparation is probably the single most time-consuming and at the same time the most important part of doing this sort of research. And it's important as well in all of these different methods to be absolutely clear that a lot of the assumptions and expectations, many of them unspoken, that are going into your research, are embedded in the data before it ever touches your software, right? I mean, it's all in there. I wonder to what degree something that people also very often say about digital methods and about quantitative methods in general is that for the historian, for the archaeologist, for the classicist, they're very good at posing new questions. They're very good at doing things like what you were saying in one of your early examples. This result is surprising. That gives us something new to explain, to explore and to examine. But the historians would often be much more cautious about saying that this digital method is going to answer our questions. To what degree would you agree with that with reference to network science?
Well, what the final sentence, would I agree? What is the exact statement I should agree with or not? I just want to make sure that
that quantitative methods are better for asking questions than for answering them.
Okay.
To oversimplify it.
Yeah. See, I knew, because I don't want to say yes or no to something I'm not particularly certain about. So I would agree that, yeah, formal methods are more appropriate for answering, for asking questions than answering them. But it's probably a combination of the two, to be honest. I don't know. It's to be. I feel this question, creates kind of a polarization between formal methods and other things that is unnecessary. Because it's interwoven. This what I'm presenting here is not. It's applied, network science. It's applied mathematics, applied physics. It's not. It's not fundamental stuff. So it's always going to be motivated by my theory, the accuracy of my data, my gut feeling as an expert in the Roman period, why a phenomena is worth studying, and what makes an important question and what makes an important answer. I think formal methods definitely have a huge advantage at being able to, surprise you quite easily. Like at the start, when I was doing network science, I used it a lot for just visualizing data, like I would do when I do GIS, like you would do when you really just have, a spreadsheet with your stuff. Every different visualization, even if it's just dry numbers or dry dots and lines, because the data means something to you, the visualization will mean something to you, and every different visualization represents something different. And so, like other formal methods, it's really good at surprising you by identifying certain features, in the case of network science, structural features that you didn't think were there, or that you are forced to think about in a different way now that you visualize it in a different way. I would also say that, the kind of more confirmative. So I've been talking a lot about exploratory network analysis, in which you have a data set and you represent it and you explore the structure of that data set. But what if you have a theory and you want to see whether a network representation of your theory fits your data very well? So you would use a method that tries to confirm whether your theory is a good theory or not. Those methods very often in the construction phase are extremely good at asking questions. So this is, again, with any formal method, but like at the point when you are forced to formalize your theory changes all the time, and your theory turns out to be underspecified, and you need to keep on specifying it. Very often the technique you use, like network science, pushes your specification in a particular direction that you didn't know you were going in before. So for asking theoretical questions, it's definitely been extremely productive. In confirmatory approaches, the output you get is always it's never, yes, the theory fits the data, or no, the theory doesn't fit the data. It's always like, with a degree of uncertainty or a probability distribution, and I think this, gives just kind of like asks more questions, raises more questions than it answers. It suggests that your theory is in the good direction, or it suggests that other theories are more probable than others, so yeah, it's definitely more no, basically I disagree with your question.
Thank you. Yeah, no, I think that's actually is a very nuanced answer, and I think that answer would probably be true of most of the quantitative methods that I had in the back of my mind. I'm not sure I've ever heard it expressed quite as eloquently as that before. So thank you very much.
Cheers.
Okay, I would have a lot more questions, but I promised Tom that he would have been off the hook by by 15 past. So I think I will just thank him once more for this very, very good tutorial and introduction. And I'll thank everyone that was watching, and for the students that are watching this as part of the module, you should have all the information that you need to perform the exercise in the links that Thomas shared in the page. So have a go at that. There is also an additional one that is, I gather, slightly more complex, but I'm sure you can make it. So thank you, everyone, and see you next week. And thank you again, Tom. Goodbye.
Thank you. Goodbye.